let's see if we can figure out what is the shape of a perfect imager. We said that you have your object space and your image space, and all you got to figure out is what is that thing that you put in between that brings all the rays together isochronous. If we can do that, we would be swimming in DARPA funds, let me tell you. So let me see if we can do it. Okay, so we need an optical axis. You almost always start with an optical axis. And let's say we have our object here, and our object is a point source of light. Let's start not too ambitious, okay? So here's our object, point source of light, and somehow we want to bring those rays together as an image. So we have one ray going along the optical axis, we have another ray going up like that, we have another ray like that. We have to bring those rays together. They do this and this at some angle and that. And they have to do it isochronous. So what are we going to do? Well, we need the optical imaging system. We need some refracting surfaces. So we're just going to draw one, right? I don't know what it is. We're going to calculate what it is. So we're saying some arbitrary surface, which we can describe as a set of points P, x, y. Right, so we're going to call this, in addition to this being the object, it's also the origin. It's a dual use label. So this is the origin, then we're up over, or going over x, up y, and P of x and y describes a surface that's going to be a perfect imager. Once we do that, we can define a couple of other things. We realize now if this is sort of the vertex of whatever this shape is, this is where it hits the optical axis. We now have a couple of important distances. The distance from the object to the front to the imaging system is SO. That's the object distance. And the distance from there to the image is SI. Okay? And we are thinking about some point on this surface, and it's always good to draw a normal straight down like that. Like that. So there's a little bit of a difference in those distances there. All right? So, and then let's see, we'll call this vertex V. Right, that's the point there. So we have our O, P, V, and I, 4 points to think about. All right, I'm going to label that for you, object distance and image distance, because it's labeled in my notes, and I have put some thought into my notes. Okay, so our job is to figure out P of xy, the P of xy that brings these rays together isochronous. So what we want to do is look at two of the rays. Let's look at, my angle didn't come out perfect, this ray that will refract like that, and this ray that will go straight through. That's the ones we care about. So what we're trying to do is make it isochronous. So what we want to do is say, if we're going to go from OPI, how long is that going to take? Well, we're in two different media, so we have to write it as two terms, right? We're going the speed of light here, we're going the speed of light over in here. So let's pretend we're making something out of glass and this is air. So we'll make the in outside air. So that would be OP over the speed of light, and then PI over the speed of light over in. Right, so it's slowed down. So that delta T for that ray has to be equal to this one, OV over the speed of light plus VI over the speed of light times N. And you may say, how could that ever be at the same time? Because this one, it looks like it's going shorter, but this one might spend more time, would spend less time in the slower medium. So there are shapes that hopefully will make it work out. Okay, so the first thing we can do is cancel the C's, right? They all are over the speed of light. So it's really just a matter of getting OP plus PI times the index equal to OV plus, oops, VI times the index. Sorry, get the I off there. All right, so let's start putting in the geometry. So O to P is this distance, oh yeah, this is absolute x squared plus y squared. So this is the square root of x squared plus y squared. That's O to P. And then N and PI. So let's see, so that's the square root of this x squared plus y squared, which isn't quite the image distance, right? Yeah, so this distance is SI. Let's see, what is this distance? This is x. It's SI plus S naught minus x, right? Is that right? Let's see. So SI plus S naught is to here, and then the point is x. Yeah, and then that's what's left, right? SI plus S naught minus x. The square root plus n times the square root of the x part, SI plus S naught minus x squared plus y squared. So those two have to be equal to, let's see, OV. OV is S naught. Okay. That's just the distance there, and it's times 1 because it's in the air. And then SI, well, this is the easy one because it's just going along the optical axis. This is N times SI. All right. And then we're actually done. That's it. This defines a Cartesian oval. That is a known shape. It's basically an egg. An egg is the perfect imager, and sort of an egg shape. So we're sort of done, right? We did it. We've come up with the perfect imaging system. And we only have one problem, and that is we have come up with a perfect imaging system inside a glass, right? Oh, this is all index n. So it's not actually that perfect. You don't want to put your eye inside of glass. That would hurt. You don't want to put a detector inside of a glass. Glass is really hard, and it's hard to melt and everything. So unless you're selling trinkets at the mall, at a kiosk somewhere, you don't really want to put images inside a glass. You really need to have the image outside of glass. So this is the perfect geometry. It's not really useful. Well, we have to think of something else.